Jai Hind students, this is my next video of satellite communication. The subject code is KAC 062 as per AKGEC curriculum, and this is a common topic which can be understood by any student who want to understand about satellite communication, and the topic is Introduction to GPS. So today in this video I will be covering main introduction or brief about GPS, also the position location principle of GPS and the GPS receiver codes that I am going to discuss today. So let's start with the basic introduction of GPS. So GPS, as we all know and we all are using in our day-to-day life, we are using GPS in our mobile phone, in our car, and it's a very day-to-day application that has been evolved, and this can be happened only because of the development in the satellite communication industry. So GPS is known as Global Positioning System, which has revolutionized the navigation and position location principle. So it is now the primary mean of navigation for mostly ships, aircraft, and it can be widely used by moving in cars or in other applications. So originally the GPS was called as Navstar earlier, and it was developed for specific military operations or military applications, and it was developed by USA. And basically in GPS, the satellite transmit L-band signals which are modulated by several codes. Okay, so there are multiple satellites which are working in collaboration with each other to provide you the facility of GPS. So we will discuss about different codes and different block diagrams of GPS today. So C by A code was made available to the public use in mid 1980s. So earlier it was originally developed only for military purpose or the defense purpose, but in early or in mid 1980s, the C by A code, that is course acquisition code, which was specifically designed for the civilian purpose. So it was made available in mid of 1980s for the civilian purpose. Whereas the high accuracy P code, which was used by the military, so that P code is known as the precision code. So it allows authorized users, mainly in military, to achieve position accuracy of 3 meters. So with the help of P code, we can get the accuracy of 3 meters. This was the accuracy for the military users who want to for the targeting smart bombs and cruise missiles. But such accuracies are also useful for auto landing aircrafts in fog and docking ships in bad weather. So I mean, not only in the defense purpose, but we can use this high accuracy in terms of auto landing systems and auto docking systems. So the first commercial use of GPS was in surveying. Okay, but by 1990 several companies have produced low cost handheld GPS receiver. So to get the application or to use that application, we should have the GPS receiver in our mobile phones or in our devices. Then only we will be able to get the services of GPS. Okay, because GPS receiver work in collaboration with the GPS satellites. Okay, so in 1990s, with the development of low cost handheld GPS receivers, it was made available for the public use. And also it has increased the sales and large volume production of this GPS receiver. The market expanded rapidly. GPS receiver are now a consumer product and can be found in everywhere. I mean, we have in mobile phone, in cars, etc. So this system has been successful because it provided direct readout of the present position of a GPS receiver with a typical accuracy of 30 meters. So if we talk about the accuracy for civilian purpose, it is 30 meters. If we talk about the accuracy for military purpose or the defense purpose, it is 3 meters. There are other position location systems which are also available, but GPS is the main application that we are using for the navigation purpose. Okay, so the success of GPS is an excellent example of what satellite do best, which is the broadcasting. An unlimited number of GPS receiver can operate simultaneously because all the GPS receiver has to locate itself to receive signal from GPS satellite. So now we will coming to the technical part of this system. So there are 24 satellites which are working in collaboration with each other in MEO or medium Earth orbit, around 21,000 kilometers from the surface of Earth, or the altitude of those 24 satellites is 20,200 kilometers from the surface of Earth, and there is some inclination which is 55 degree inclination is also there in these satellites. These satellites are clustered in a group of 4. So total satellites are 24, and at a time we need 4 satellite signals. So we group the satellite into 4. So this grouping of satellite is known as the constellation, with each constellation separated by 60 degree in longitude. So total 24 satellite, 4 satellite will be working as a cluster. So total 6 clusters are available, and these clusters are 60 degree separated in terms of longitude. And the orbital period means the overall time which the satellite took to rotate around Earth is 1/2 of a sidereal day, that is 11 hours and 58 minutes. So the same satellite appear in the same position in the sky twice each day, because the total orbital time of Earth is 24 hours. So it is just half of that. So you can see that satellite twice in one day. The satellites carry station keeping fuel and are maintained by, in the required orbit by occasional station keeping maneuvers, just like geo satellites. So this is a GPS satellite. This is a picture of original GPS satellite. Okay, so as I told you, 24 satellite will be working to provide you the facility, and 24 satellite will be covering the complete world to give the application of GPS. And at a time, a GPS receiver can see 10 satellites. Okay, so my GPS receiver at this time can receive maximum of 10 signals from 10 satellites, right? Not always we are getting 10, but yes, at the max we can get signal from 10 satellites. Replacement of satellites are launched as needed, so that there can be more than 24 satellites operational. So what we do, because we need at least 24 satellites to provide the full coverage, so there are few additional satellites that we launch for as a backup purpose, so that we have operational 24 satellites which are providing you the facility of application. So we'll see in the next picture. We have seen the picture of GPS satellite. The weight of satellite is around 1,877 kgs at the launching time, and the lifetime of this satellite is 10 years. GPS system is operated by US Air Force from the GPS Master Control Station. So there is a Master Control Station, MCS, which is located in USA, which will be controlling the overall operation of GPS around the world. The position of GPS receiver is found by trilateration, which is one of the simplest and most accurate method of locating an unknown position. So what we are using for the position location principle, we are using the trilateration method. And what is this trilateration method? That I'll be covering in the next slide. So with the help of this method, we can locate any GPS receiver anywhere in the world. So what is this trilateration? In trilateration, the distance of unknown point from 3 known points is measured. So there is one unknown point. For that I need to guess the location. So distance of this one unknown point can be measured with the help of the position of 3 known points. Okay, and the intersection of arc will give you the point where your GPS receiver is located. So the intersection of arc corresponding to 3 distances defines the unknown position relative to the known points. Since 3 measurements can be used to solve 3 equations, will give the latitude, longitude and the elevation of the receiver. The distance between the transmitter and receiver can be found by measuring the time it will take for an RF pulse or RF energy to travel between the two. So how we will calculate the distance? We will calculate the distance by sending one RF pulse, and we know the speed of that electromagnetic wave, and then we can calculate the distance. Now the distance is calculated using the velocity of EM wave in free space, which is approximately 3 × 10⁸ meter per second, and more accurately, this is the velocity of light. So time can be measured electronically more accurately than any other parameter by the use of atomic clocks. So this is a very important point, that we are using atomic clocks on the satellite because we want to have the timing accuracy. If there is some change, slight change in time, then it will affect the distance, and then afterwards it will affect the position location accuracy also. So because of that, this timing information must be highly accurate, and because of that, what we are using atomic clocks on the satellite. Okay, so now I'll be covering how the GPS position location is calculated. All the GPS satellites are synchronized with each other, and the synchronization and the calibration is controlled with the help of master control station. So what it will do, let me just go through with this. Yes, so this is a picture. So how we will calculate the position of a GPS receiver? Here we have the GPS receiver, okay, and we want to calculate where this GPS receiver is located. How we will calculate? We have 4 satellites from where we are receiving the signal, right? And also we know where this satellite is located. How we know that this satellite is located? Because these satellites are transmitting codes every second, with the interval of very few seconds. They are sending the codes to us, and this receiver will be receiving the codes, and in this code the satellite is transmitting its position, current position. So current position of the satellite is known to us, and at what time that information is sent, that is also known to us. So in that way we can calculate, okay, at T1 time this satellite is located at this point. Similarly, at T1 time this satellite is located at this point, and this satellite is located at this point. So we know the exact position and time of the satellite because we are receiving the code from satellite. Okay, so we know the time, we know the velocity, so can we calculate the distance? So in that way we can calculate the distance between the satellite and the unknown position. Similarly, the distance from this satellite will also be known, okay, and distance from this satellite will also be known, distance from this satellite will also be known. And in the in this coordinate geometry, you must have studied about this equation. Okay, in coordinate geometry you have studied like how you can calculate the distance between 2 points where one point is known and another point is unknown, right? So the distance r between 2 point A and B in a rectangular coordinate system can be calculated as r square is equals to xa minus xb whole square plus ya minus yb whole square plus za minus zb whole square, right? So in that way our receiver is ux, uy, uz coordinates. Okay, here my receiver which is having ux, uy and uz coordinate, and these are 4 satellite S1, S2, S3 and S4, right? So distance from S1 to ux is PR1, distance from S2 to ux, uy, uz is PR2, likewise PR3 and PR4, right? So the first equation, if I would like to draw, is from S1 to this unknown position, this GPS receiver U. So the equation will be x1 minus ux whole square plus y1 minus uy whole square plus z1 minus uz whole square. So ideally it should be PR1 square, right? But here one point is to be mentioned, which is the tau c. So this tau c is actually the offset error. So what is that offset error? Offset error is actually there is a slight difference between the clocks which are available on the satellite and the clocks which are there with the GPS receiver. So these clocks are not calibrated with each other highly accurate, because there would be some error in these clocks. So because of that error, what we have done, we have introduced this tau, which is the timing offset error. So this error is introduced here. Okay, so that is why we can say that there can be a change in the distance. So that is why this distance is PR1 minus tau c whole square, right? Similarly, for 4 consecutive equations we have drawn PR2 minus tau c whole square likewise, and this tau is known as the receiver clock error or the offset or the bias. So with the help of these 4 equations, okay, 1, 2, 3, 4, what we will do, we will calculate the unknown parameters. So we have three unknown parameters, ux, uy, uz, and the fourth unknown parameter is the tau. So that is why we need to have signals at least from 4 satellites. 3 satellites will be used to calculate the distance ux, uy, uz, and the fourth satellite information is used to calculate the tau. Okay. So for this system, what we are using a coordinate system ECEF. So ECEF is Earth centered, Earth fixed coordinate system that we are using here, and the coordinate that I have used is ux, uy, uz, and x1, x2, x3, y1, y2, y3. These are the coordinate of the satellites. Okay. The position of satellite at any instant is sent the timing signal, which is obtained from ephemeris data transmitted along with the timing signal. So timing information is sent, and actually the ephemeris data is also sent. So because of that, we can calculate the position of satellite. Each satellite send out a data stream that includes the ephemeris data for itself and the adjacent satellite. So the satellite which is giving you a signal, it is giving the information about itself and also about the nearby satellites. Now the receiver will calculate the coordinates of the satellite relative to the center of the earth, which are xi, yi, and zi, and then solves 4 ranging equations. So these equations are known as ranging equations. These are called as ranging equation. So if a question can come, what are the ranging equations, then you have to draw the picture and you have to explain these 4 equations, which are known as ranging equations. And this method of calculation is known as trilateration method, also the GPS position location principle. Right. So these ranging equations are calculated, and the 4 parameters or 4 unknown values are also calculated, and the 4 unknowns are the location of GPS receiver related to the center of the earth and the clock offset, which is also known as clock bias. The receiver position is then referenced to the surface of earth and then can be displayed in terms of latitude, longitude, and elevation. As you can see that whenever you are sending a location of yourself or someone else, it is always represented in terms of latitude, longitude, and the elevation. So 3 parameters will give you the information about latitude, longitude, and elevation, and the 4th parameter will be giving you the information about the timing offset error. Okay, so GPS time is the clock bias value, which is found as part of the position location calculation process, can be added to GPS receiver clock time to yield a time measurement that is synchronized to the GPS timing standard. So GPS time is the clock bias value, which is tau. It will be added to the receiver clock. Like in my phone, I have GPS receiver. But yes, in my phone, whatever clock I am using, it is not the atomic clock. On GPS satellite, we have the atomic clocks, which are highly accurate. So that is why these clocks are not synchronized. So how this synchronization is done? This synchronization is done with the help of this clock bias value. This clock bias value will be added to the GPS receiver clock, and then it will be synchronized with the GPS timing standard globally. Now, the crystal oscillator used in GPS receiver is highly stable over a few seconds, but it will have a frequency which changes with temperature and with time. Temperature changes causes the quartz crystal, that is a frequency determining element of a crystal oscillator, to expand or contract, and this changes the oscillation frequency. So what we are saying, like in our GPS receiver, normal crystal oscillator is used, and what we do in crystal oscillator? In crystal oscillator, there is a frequency which is generated, and that frequency is representing your clock. Okay, so because of the change in temperature, this clock frequency will be varied, and because of that there can be some error. So that is why we need to synchronize our GPS receiver with the global time. So that can be done with the help of adding that clock offset with the actual GPS receiver time. Now, the next topic is the GPS receiver and codes. So, in short, I'll tell you what are the GPS receiver and codes. So, there are 2 type of signals that we can see in GPS satellite, L1 signal and L2 signal. So, L1 frequency is actually used by the normal civilian people. L2 frequency is used by the military applications. Okay, so L1 is the signal, and it is containing the codes. So the codes that I have already told you, there are two type of code, P code and C by A code. Okay, so in L1 signal, majorly we will be having C by A code and also few part of P code. Okay, whereas in L2 signal we will be having only and only P code. So L2 signal will be used for defense purpose, L1 signal will be used for civilian purpose. Okay, GPS satellite transmit using pseudo random codes. So what are the pseudo random codes? PN code. So as we all know that in GPS this operation, the scheme, that the coding scheme that we are using is the CDMA. CDMA we are using. And what is this CDMA? In CDMA, we have two type of CDMA strategies, direct sequence spread spectrum and frequency hop. So here we are using direct sequence spread spectrum. Why we are using direct sequence spread spectrum? Because of the advantage, or because of the main focus of this DSSS is that it provides you the highly accurate information. Highly accurate information in the sense that whatever signal we are transmitting, that signal will be multiplied with a long sequence code, and that long sequence code is also known as the PN code. So whatever signal satellite is transmitting, it will be multiplied with the pseudo random code or the PN code. Okay, and all satellite transmit a C by A code at the same carrier frequency, which is 1575.42 megahertz, which is called L1, and we are using BPSK modulation here. Okay, so first your signal will be multiplied with the 1575.42 carrier frequency, and then it is converted into CDMA code, and then we will do the BPSK modulation here. The L1 frequency is 154 times the master clock frequency of 10.23 megahertz. The C by A code has a clock rate of 1.023 megahertz, and the code sequence has 1023 bits. So the PN sequence lasts exactly 1 millisecond. So the length of code is 1 millisecond, and in one code we have 1023 bits. Okay, we have 1023 bits which are available in one C by A code. The exact value of the frequencies are about 0.005 hertz lower than the stated here, to allow for a relativistic effect caused by the high velocity. So there can be few difference in between the frequency which is mentioned here. Next is the P code. The P code is transmitted using BPSK modulation at the L2 carrier frequency of 1227.6 megahertz. So the L2 signal will be having will be kept at 1227.6 megahertz, which is 120 times the master clock frequency, and also the master clock frequency is 10.23 megahertz, and is also transmitted with BPSK modulation on the L1 carrier frequency in phase quadrature with C by A code BPSK modulation. So that I'll be covering in next slide. So basically in L2 signal, what we are having the P code. Okay, and the carrier frequency of this L2 signal is 1227.6 megahertz. Now the C code and C by A code and P code transmission from all GPS satellites are overlaid in the L1 and L2 frequency band, making GPS a direct sequence spread spectrum signal. Okay, so what satellite is transmitting? It is transmitting both the signals, L1 signal and L2 signal. Okay, and whatever is the requirement of the GPS receiver, it will extract that information. Means if it is required by some defense purpose, then they will extract the L2 signal. If it is required by some civilian operation, then it will be extracted, it will extract the L1 signal. Almost 12 GPS satellite can be seen via receiver at any one time. Okay, so the coding gain in the spread spectrum receiver must be sufficient to overcome the interference caused by the unwanted signal. So as we know that a max of 10 to 12 satellite signals can be received at one time by a GPS receiver. So it should have the high correlation factor, so that it can easily overcome the interference which is caused by the unwanted signals from other satellites, because we want only 4 signals at a time. So rest 8 signals will be the unwanted signal. So your receiver should have the capability to overcome the effect of interference caused by those unwanted signals from other satellites. So this is the signal generation in a GPS satellite. As I told you that we have two type of signals that we are transmitting. So these two signals are transmitted by a GPS satellite every time. So the satellite is transmitting this signal every time, right? Okay, so both signals are transmitted. So if we want to have the signal which we want to use for civilian purpose, we will be using this L1 signal. And if we want to use the signal for military application, then we will using the L2 signal. So you can see the output. Okay, first we will see what we are desired for. So in L1 signal, what we are desiring, we wanted to have L1 plus P code plus C by A code plus navigation package. So it's a complete package. So this complete package of L1 output will give you the L1 signal plus P code plus C by A code plus navigation information. Navigation information means the position of satellite, right? The current position of satellite, live position of satellite. In L2, we have the L2 signal, the P signal and the navigation. So this is for the military application or the defense application. This is for the civilian application. So here you can see that how we are designing the codes. First we have L1, C by A code, navigation message, P code and L2. L1 and L2 are the carrier signal and we have kept a frequency. L1 carrier frequency is 1575 megahertz and L2 carrier frequency is 1227 megahertz. Okay, and the modulation scheme that we are using here is the BPSK modulation. C by A code is generated. There would be some other circuitry to generate the C by A code, and there would be some other circuitry to generate the P by A code. So here we are looking like we have the P code and C by A code available, right? So here this L1 signal is given to this pi by 2 block, and then in phase part is given to this multiplier. So the phase quadrature part is given to here. So as we know that this in L1 signal, your C by A code is the quadrature part of this signal. So that's why we have given this LY signal, and this is C by A plus navigation is given to this. C by A plus navigation means C by A code is generated here and navigation code is generated here. So we have multiplied these two. After multiplication, we have given this to the quadrature part. Similarly, this L1 in phase part, we are giving the P plus navigation. P plus navigation means P code is given to this multiplier and navigation message is also given here. So P plus navigation is coming from this place to this place. So in phase part is this one, in which we have the P plus navigation, and in quadrature part we have the C by A code plus navigation. So the output will be C by A plus navigation, P plus navigation, right? And L is also there. So L1 plus P plus C by A plus navigation will be the first part. Now coming to the below one, where we want to generate the L2 signal. So in L2 signal, first we are having the in phase part. Okay, so in this L2 signal, we don't want to have C by A code. There is no need to have the C by A code. We only wanted to have the P code. So this will be only in phase part will be there. There will not be any quadrature phase part here. So this P plus navigation will be given and it will be multiplied by the L2. Okay, modulation is done. PPSK modulation here we are doing, and the output will be L2 output, which will be having the L2 signal, which is coming from here, plus P plus navigation. So the final output will be the combination of these two signals, right? So this is how the signal is generated in GPS satellite. This I have already covered here. Now coming to the C by A code generator. How the C by A code is generated in a GPS satellite. So we have discussed about the navigation principle. We have discussed about how the signals are generated, L1 and L2 signal. Now we are coming to the how the code is generated, C by A code. See, here I have taken this C by A code block as it is. So now I am coming to the background of this, how this C by A code is generated. So there is nothing much in the C by A code. Very simply, what we are having the combination of shift registers. So here you can see that in the C by A code we are having 10-bit shift register, okay, 10-bit shift register G1 and 10-bit shift register G2, okay. So output will be C by A code and clock. We are also receiving the two different clocks. So here we have X1 signal which we are resetting it to 1. Then this is the master clock frequency, and as we know that the master clock frequency is 10.23 megahertz and the clock frequency of C by A code is 1.023 megahertz. So to get 1.023, what we need to do? We need to divide this frequency by 10, right? So this we have done. Now this signal is given to these two shift registers. So this is the clock frequency which is given to these two shift registers to enable them, okay. And then here we are giving the signal. So we have reset both the signal to 1. Okay, now we have some feedback taps available. So these feedback taps are just provided what sequence we want to generate. I mean, if we want to generate 1 0 1 1 1 or we want to generate 0 1 1 1, so any combination we can generate with the help of these feedback taps. So this is how this C by A code clock frequency are generated in the C by A code. Okay, so bit pattern is set by the feedback taps and combining logic of shift registers. The PN sequence G1 and G2 are both generated by 10-bit shift registers and are therefore the length is 1023 bit. Okay, an n-bit shift register can generate 2 raised to the power n minus 1 bit length. The clock rate of C by A code is 1.023 megahertz. So the sequence will last up to 1 millisecond. The C by A code for a particular satellite is created with an algorithm that includes the identification number of GPS satellite, thus creating a unique code for each satellite. Okay, so there will be a unique code for each satellite. What we are doing, we are giving some ID number to each satellite. So the satellite ID number I has a C by A code sequence CIT. Like for first satellite, it will be C1T, second satellite C2T, third satellite C3T. So the coding will be done like this. CIT will be G1T into G2 T plus 10 ITC, and TC is the clock period of C by A code. So a total of 100 gold sequence can be generated or created using this algorithm. Okay, but not all sequences have sufficiently low cross correlation properties. And reference 4 states that only 37 are accurately used in the GPS system. So we can generate 100 of codes with the help of this equation, but yes, these codes must have low cross correlation. Okay, by low cross correlation, so that we can identify different codes for different satellite. If there will be a high cross correlation factor, then we cannot differentiate two different sequences. So that's all for today. Thank you very much.